Okay, good morning. Welcome to Thursday. I'm off to a really good start this morning. I remembered to turn the projectors on. So I'd like to pick up where we were on Tuesday. We were talking about defining your own functions. And in general, to define a function, you use the keyword def. Following that, you give the name that you want your function to have, which can be any valid identifier. And then inside parentheses, you specify the parameters that you want the function to be able to make use of. And those have to be ordered with positional parameters coming first and keyword parameters, if any, coming afterward. All right, we saw that there's a special positional argument that you can use, which by convention is named star args, but you could call it star xyz or whatever you want. If you use that special positional argument, it has to be last in your positional argument list, and that will be a tuple of all of the trailing arguments that the user types after whatever required positional arguments the function expects. So far, so good? Okay. Now, you can also pass a varying number of keyword arguments. The conventional name for this variable is star star. Well, the star star is required syntax for this. The usual variable name is KW args for keyword args, but there again, you can pick whatever you want. And if you use that special variable, it has to be at the very end of the argument list after any other keyword parameters that you create. All right, so here I have a little function named VF2 showing the order in which you need to specify these different kinds of parameters. I have my required positional parameter first, and then I have star args for the optional additional positional parameters that will be wrapped into a tuple. Then I have an explicitly named keyword parameter, B, whose value is 42. What is 42, by the way? Sorry? Absolutely, yes. Yes, 42 is the meaning of life, or is the answer to the question of life and universe and everything, yes. All right, stupid sci-fi reference. And then following that list of named parameters, you can have the KW args, which will contain any additional named parameters that the user specifies when the user calls this function. All right, so let me actually define this thing, and we'll just use print to exercise it. So I'm going to, type this thing into my, okay, so def VF2. All right, so VF2 is my function. It takes one required positional parameter that we're going to call A, and then star args for any additional. Then it has one named keyword parameter, B, and optional additional keyword arguments. And all I'm going to do to illustrate how this works is to display A, args, B, and KW args using the print function. Now, whereas args is a tuple of the additional arguments that the user types, KW args, it turns out, is a dictionary where the keyword parameter names are the keys and the values assigned to those keyword parameter names are the values. This allows me to make up any keyword argument names that I want, and they become part of the dictionary that's passed in. All right, so if I run this by saying VF2, 1, 2, 3, 4, let's say x equals high y equals 123, z equals true. Okay, what's going to happen now is that a, the parameter a, is going to receive the first positional argument. So a is going to be set to 1. Args is going to be a tuple containing the trailing positional arguments. So so args is going to contain 2, 3, 4 as a tuple. Now b is a keyword arg that I defined in my function with a default value of 42. And in my call of the function, I haven't specified a different value of b, so b will be 42 by default. But I have given 3 more keyword parameter names with the values I want those to have. And so those are going to be thrown into a dictionary named kwargs. And there we are. So I print the value of a, which is just the value 1. Then I print args, which is this tuple, 2, 3, 4. Then I print b, which, because I didn't say b equals something in my call, is the default value 42. And then kwargs, as you can see from the curly braces and the colons here, this thing is a dictionary with x, y, and z as the keys, high, 123, and true as the values associated with those keys. Good? All right. So far, most of the stuff that we've been doing, in fact, I think all of the code that I've shown you, has been in a single source code file. We have used the math module by importing the math module, but we would like now to be able to define modules of our own so that we can have those in our back pocket for use for future programming work, and so that we could share these modules with other Python programmers. When you define a module is basically just a file containing Python code, and that module can be imported into other programs using the import statement, as we've talked about. Now, every what am I trying to say here? All of the Python code that you execute is considered to be in a module. The main module is really just the first module of code that you start running, and then that module of code may import other modules. Now, the shell itself thinks of itself as executing a module of code. It's just that in this case, the module of code is the code that you're interactively typing. And the shell always thinks of itself as the main module. Okay, so in my shell, when I say something like print 1234, the shell thinks, okay, I'm the main module and I'm going to execute this print statement. There's a special variable available in Python that will tell you the name of the current module that's being executed. And the value of that special, or the name of that special variable is underscore underscore name underscore underscore. Okay, underscore underscore name underscore underscore is too hard to say. It's sort of like the there's an old joke or complaint or something about the web that what was it, Berners-Lee, I've forgotten his exact name, created an acronym for the World Wide Web, which has more syllables than the World Wide Web does. WWW is 9 syllables, whereas World Wide Web is just 1. And so we got the same kind of problem here. Underscore, underscore, name, underscore, underscore is just too painful. So what a lot of people do with names like this that start with 2 underscores is to call them, well, double underscore names, but of course that's too long also. So they're called dunder names. So the dunder name of this special variable is underscore underscore name underscore underscore. Okay, and as you can see, the value of dunder name here is underscore underscore main underscore underscore or dunder main. So that tells you that yes, the shell believes that it is the main module. Okay, now in a module you can put things like variable definitions. When we imported math, you may recall that we had the value of pi available. So that's an example of a variable that was defined in the math module. You can also have function definitions, and we saw in math things like cosine and exp and sine, and I don't think I showed you this, but log and arctangent and all these other things. You can also put classes in modules, and defining classes of our own is going to be something that we're just going to barely describe in the last day. That's a little bit beyond what I have time to ask you to actually do. But these are the kinds of things, variables, functions, and classes, that you would find in a module of code. Now, the name of the module that you use with the import statement is exactly the same as the name of the source code file containing the module, except that you just leave off the .py extension. So if I define a module of code with variables and functions and classes, and I have that in a code file called mystuff.py, then to access that stuff in another program, I would say import mystuff. Okay? Now, if you accidentally say import mystuff.py, Python gets confused and it goes out looking for a file whose name is mystuff.py.py. And there is no file called mystuff.py.py, so you get an error. So in the import statement, leave the .py off, even though you have to have the .py extension when you define the code. Okay? Okay. So I've talked about dunder name, which is the special variable that you can look at within a module to find out what the name of the module is. I also want to point out to you that there's a function, vars, that will report to you a dictionary of all of the global stuff within your current module. And if I'm interactively in the shell and I type vars, what I get are all of the global variables that the shell knows about. Now, when you look at the global variables for any module, the very first one in the dictionary is going to be dunder name with its value, which in our case is dunder main for the shell. And then we have all kinds of other sort of built-in things for Python, like documentation, package, loader, blah, 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 file. That's a file that I have that I had previously edited. And you can see from Thursday I still have agebad and agestir sitting around. And then I also have the things that I've just created today, namely the x variable and the vf2 function. Okay? This is actually a fairly short list. Usually if you're involved in a complex long Python session, this dictionary is going to be huge. All right, so let's suppose that I define a program file called mymodule.py, and in that program file I define some functions, I define some variables. Maybe one of these functions is called fun1, maybe one of these variables is called cnum for a character representation of a number. It's a string. Then if I want to add testing code, internally within my module so that I can test whether the module itself is working, what I can do is to say, at the bottom of all my code, I say if dunder name is equal to the string dunder main, well, that means that I am currently editing and executing this file itself, and so I can put testing code down here to do a test call of fun1 and display the value of cnum. So this is a very common structure. When you define a module of code, at the bottom of the module of code, you'll have a test like this. If dunder name equals dunder main, then do some testing. But if you import my module into some other program, then when the contents of my module is executed, my module is not the main module. The main module is the one that imported my module. And so in that case, if my module has been imported, dunder name within my module will be my module, not dunder main. All right, that's very kind of hand-wavy and theoretical. Let's see a specific example. All right, I have, and this is available for you to look at on Canvas, a code file called mymath.py. And I have loaded that into my editor in idle. Okay, so here is mymath.py. And in here, I've got three simple function definitions. I'm defining the square root function to compute x to the 0.5 power and return it. I've got the cube function that computes and returns x cubed. And I've got the mysum function, which we looked at on Tuesday, which just does this very simple-minded sum of some arbitrary number of numeric arguments. Now, I could just have that be my code. I could just define this as my module and allow other people to import the module and use these functions. But it's generally a really bad idea to write functions and then give them to people without having tested them. So to protect myself and the people I want to give this to, at the bottom of my file, I'm going to put in some testing code. So if dunder name is main, then I'm going to test the square root function, the cube function, and the mysum function to see whether they do something that makes sense. I'm also going to display the name of the current module. On the other hand, if dunder name is not equal to dunder main, that means that this file has been imported by some other file, some other module, and in that case, I am going to execute this else part saying that the imported module name is, and whatever dunder name is in that case. Okay, do you agree that I am currently editing this file? All right, so this file is my main module if I execute this file. So I'm going to do that. I'm going to say run module, and cool. All right. This is the main module. This file that I'm editing is the main module, and so square root was defined, cube was defined, mysum was defined, and then we discovered that dunder name was equal to main, so we executed the print statements contained within that if part, and we printed out that module name is dunder main, square root of 3 is 1.7, blah blah, 12 cubed is 1728, and the sum of these values is 30. So our test code was executed because dunder name was dunder main. Now, on the other hand, let's suppose that I have a separate program, separate code file. This is called myprog.py. And in myprog, I want to make use of some of the functions that were defined for me in my math. So I'm going to say import my math as the name, as the abbreviated name mm. Notice that I don't say import mymath.py. I have to leave the .py off. But Python will go out looking for a file named mymath.py and suck in and execute the entire contents of that mymath.py file in place of that import statement. So after mymath has been sucked in and executed, I'm then going to create a variable x referring to 123. And this time around, because my prog is the main module if I'm executing my prog, I will execute these print statements. All right, so let me pull up my prog. And so now I'm editing my prog, and so if I say run module, my prog.py is the current main module. And this import statement goes out and finds mymath.py and pulls it in and executes everything inside there. Now, executing everything inside mymath means defining the three functions. What were they? Square root, cube, and sum. Square root, cube, and my sum, I guess. And at the bottom of that mymath.py program, notice that there's this else here. The else gets executed if mymath is not the main module. And in this case, my prog is the main module. Consequently, the else in my math gets executed, and that's where I'm getting this line of output. The imported module name is my math. Okay? Then back in my prog, I get told module name is dunder name here is going to be main. And then I get told 123 cubed is whatever it is, and the square root of 123 is whatever it is. All right, so this import was executed, and that import sucked in the copy of mymath.py, defined square root, defined cube, defined my sum, and then discovered, oh, dunder name is not dunder main. Did I say that right? Dunder name is not dunder main, so I'll print the name of the module, which is my math. All right, so that happens. So the printing of my math happens as a consequence of doing the import. Then I define x equal to 123 and call these three print statements in my prog program. Any questions about what's going on here? It's kind of, until you do it yourself a couple of times, it's maybe a little, well, you have to do it a couple of times and it will make sense. Any questions? Yeah?
I was wondering, what's the best practice of naming the modules?
Well, okay, so I don't know if there's like a Python-wide rule about this, but the name of the module should be meaningful. It should describe what the module does. It should be long enough so that it doesn't conflict with other module names, but it should also be short enough that people are willing to type it. I guess that's about all I can really say about it.
Like in C#, do we have like a main, which is the function that you run to execute everything?
Yeah. Well, okay, so in Python we don't have something equivalent to a main function. So you're saying in C# you would have something like main dot whatever. There's nothing preventing you from doing that in Python. You could create a module called main.py for each project that you write. I guess that's up to you to decide what you want to do. I'm not sure that there is such a convention in Python. Other questions? Yeah.
Can you think of a trivial example where it might be useful to like within a program know the name of the module?
Generally speaking, the most common case is the case that we've shown here, where you have at the bottom of each code file that you write this test to say if _name is main, that means that this is the file that I'm directly editing and executing, and so I put test code underneath there. But you're right that generally, other than testing whether the name is main, there isn't really much reason for a module to ask, gosh, what is my actual name? Or for a program to ask, gosh, I just did an import of foo. I wonder what the name of that foo module is that I just imported. Well, better be foo. So this is the far and away the most common case. Yes?
So if you have multiple imported modules, what happens to them?
Well, okay, excellent question. If I have multiple imported modules, let me just show you. Let's do another one here. Import mod2 as m2, and let me quickly create such a module. Okay, so this is a stupid little module, and all it does is to define a variable name. In here, I can have my, I can say if _name is equal to _main, print, come on. Come on, type. There we go. Okay, so this is the module that I'm currently executing, or that I'm currently editing, and so I'm going to save this as mymod2. Did I call it mymod2 or just plain mod2? Mod2. Mod2.py. Okay, so this is mod2.py, and if I execute it, if I'm executing mymod2, then it is the main module. If I'm executing myprog, on the other hand, within mod2, _name is mod2. Within mymath, _name is mymath, and within myprog, _name is going to be main. So there isn't any confusion. You can never have a situation where you have multiple modules with the same name, because each file has to have a different name, or you can't have two files with the same name in the same directory. But I can say print mod2's Farkle Was that sufficient?
More so, what kind of object is name? Because if you do name, you have to check for mymath and mod2. Check whether it equals name. Or am I missing something?
Ask me that question again.
Like, what kind of object is name?
What kind of object is _name?
Yeah.
A string.
Okay.
Oh, I'm sorry. Sorry. That's my dog feeding alarm. Okay, good. Other questions? Yes.
So, when would be a good time to see this model into fact? Because I'm thinking we could literally do the same functions of like using cubes and square roots, just defining our functions. So when would we prefer to have a model and import it as opposed to just defining our functions in the side?
Okay, really good question. When would you prefer to import a module as opposed to just defining the functions yourself? Well, I mean, the obvious answer is if the contents of the module are complicated, and it would be time-consuming and error-prone for you to redefine those same functions yourself, then you're much better off importing a module. For example, if you want an accurate value for pi, and you want an accurate value for e, it's a lot easier to import math rather than manually typing out your own representations of those values, because you're going to flip a couple of digits by accident if you type it yourself. And also, of course, there are very complex statistical and machine learning kinds of algorithms, and you wouldn't want to have to manually type that stuff in yourself. Other questions? Okay. So let us continue. Okay, so for our purposes, it will be fine to just have all of our code files in the same directory, so that the main code file can simply import the other code files, and you don't have to worry about things like directory paths and stuff like that. It is possible to get much more sophisticated about, about how your modules can be organized into a hierarchy, and you can use environment variables, you can set up configuration files, and all kinds of other administrative stuff, but I'm not going to expect you to worry about doing all that. All right, so the second half of this material is going to be a quick introduction to NumPy. NumPy is one of many very widely used, very powerful modules for things like linear algebra, statistics, spreadsheet-oriented operations, machine learning analysis, and so on. And we are going to use the naming convention that you'll see if you look at online documentation or books for these various modules. In this, the rest of today, we're just going to look at NumPy, and we're going to import NumPy using the abbreviation NP. Almost always, if you look up NumPy examples online, or if you look at examples of NumPy in books, NP is the abbreviation that people use. And then next week we'll look at pandas, and we may look at some of these other ones as well. Okay, so NumPy supports a data type called ND-array. ND-array stands for n-dimensional array. And it's a little bit like a list, but it's much faster than a list, because it turns out that NumPy is directly implemented in the C language, which is inherently much, much faster than the higher level collection types in Python, like lists and tuples and sets. All right, so syntactically, though, dealing with NumPys is intended to be similar to dealing with lists, so that you don't have to learn radically different notation. If I wanted to create a list of a sequence of 5 values from 0 to 4, I could just say that. Create a list using the iterable range 5, and that's going to give me back a list of 0, 1, 2, 3, 4. If I import NumPy as NP, then I can say, come on. Okay, NumPy is fairly large. And my laptop is getting old, so it takes a while to suck that thing in. If I say A gets np.arange 5, arange creates an array like the range function does of values between 0 and 4. All right, so basically the same values that I got by asking for a list from the range 5. I had to remember, because this is a NumPy facility, I had to remember to use my NP module abbreviation before I did that. Now, I could have said numpy.arange. That will, of course, work, but... Oh, no, it won't. Oh, interesting. That's right. If you import a module and use an abbreviation, then the actual original name is not available. Okay, I'd forgotten that little detail. So A gets np.arange is how I can create an ND array. Now, to access or to iterate through the items in an ND array is very similar to accessing or iterating through things in a list. For example, if I say m sub 2, I get the sub 2 item from m. You know, it just dawned on me that this is kind of an unfortunate example because the indexes are the same as the values. Let me do something a little smarter and say m gets list range going from 5 to 0 with a step of -1. Even that's not going to work very well. So let me 15, 2. All right, that's a little more interesting. 5, 7, 9, 11, 13. So m sub 2 is going to be the 9. And I can do the same thing with a range. I can say np a gets np.arange, takes the same kinds of arguments with the same meaning. And now a sub 2 is 9. Okay, so the arange function takes an initial value, one past the final value, and a step, just like the range function does. And I can subscript within a, just like I can subscript within m. You can also use negative subscripts in the same way. So a sub -1 is going to be 13 in this case. However, you do not have the arbitrary precision integers available in an ND array that you have in Python. For efficiency and representation in memory, the integer values in ND array are restricted to 32 bits, which means that they'll have values roughly between plus and minus 2 billion. All right, this is the same range of values for an int in a C or C++ program. All right, so the type of m is list. The type of an item of m is int. The type of a is ND array. And the type of a sub 0 is not int, it is numpy int 32. All right, so if I try to say m sub 0 gets 2 to the 1,000th power, that's going to be fine. Now m sub 0 is this giant integer value. Well, not so giant. I meant to do an exponent and I did a multiplication. Oopsie. Let's try that again. M to the 1,000th power. Okay. But I can't do that with A. If I say A sub 0 gets 2 to the 1,000th power, I'm going to get an overflow error. that Python integer value, 2 to the 1,000th power, is too big to convert into a C language long integer. Now, it turns out that because we're using 64-bit laptops, that a long integer and an integer are both 32 bits. They're both the same size. On older systems, it used to be that a long integer was 32 bits and integers were 16 bits. What's the year? So what I'm describing was 38 years ago. We haven't had 16-bit integers on machines for a very, very, very long time. But the point is that you have a more restricted range of values that you can fit into a NumPy ND array. Now, an ND array is iterable, so I can easily create a tuple from an ND array, and I can easily create a list from an ND array, and I can easily create another ND array from an ND array. Here is the NumPy function that expects an iterable and that produces an ND array from that iterable. All right, so T is a tuple, M2 is a list, A2 is an ND array. That iterable, of course, that I use to create an ND array could be a list or a tuple or a set or something else. Now, for floating point numbers, again, we have a restricted range of precisions and magnitudes. However, it turns out that the restricted range is identical to Python's own restricted range, so this is not really a problem. All right, so I'm saying here A3 gets np.array, and just for gags, I'm using a tuple as my iterable here, 3.14159 and 2.71828. Okay, so notice that I have a tuple in there. Those are the inner parentheses is creating a tuple, and the outer parentheses are the function call. And now I have A3 as an ND array of two floats. The type of these floats is NumPy float64. Now, float64 means that it's a 64-bit wide or an 8-byte wide floating point number, and that's exactly the same representation as floats in Python. So, at least in this release of Python, it's guaranteed that you can take a C language double precision floating point number and put that into a Python float and vice versa, and that won't change the value. Now, a list, and this is true of Python collections in general, a list or a tuple or a set, can have mixed type of items. But in an ND array, each item has to be the same data type. And again, this is a restriction intended to improve efficiency. If you try to create an ND array using mixed data types, the ND array creation will use something called upcasting, which is that the ND array creation will identify what the most complicated data type is of the various things in the iterable, and it will then try to convert all the less complicated things up to the most complicated thing. In this particular example on slide 43, we're not doing anything too complicated. We're saying A4 gets an array, an ND array, built from this list, 3, 4.5, comma, 6, comma, 7.8. So notice that this list has mixed data types. 2 of these items are ints, 2 of these items are floats, and so the ND array creation will say, well, floats are more complicated than ints, so I'm going to convert the ints to floats, and everything will be represented in A4 as a floating point value. All right, so I've got 3 point and 6 point in here, so that all of the items in there are floating point. I can, that thing is an iterable, so I can say for V in A4, print V and the type of V. Okay, so 3.0 is a NumPy float 64, 4.5 is float 64, etc. Make sense? It's always the wrong question. I have this habit of asking, does it make sense? But do you understand is the relevant question. Yes?
So earlier we're trying to do 2 to the power of, let's say, 10 or 100. But does that also mean that every other element in that ND array will also have the same length?
Every item in an ND array is going to be the same data type, and therefore it's going to occupy the same amount of memory, and it's going to have the same bit pattern representation. I think there was more to your question, though.
No, I was just wondering, because if we converted, let's say, one element of the ND array, does that also mean that all of them will also occupy? So, for example,
Oh, if you converted one element of the ND array?
so instead of, let's say, 3, 4, 5, and 6, if you do 30, so it will be 0, 4 instead of this 4.
Tell me what to type so that I answer your question exactly.
So let's say there is this 3, 4, 5, and 6, right?
So I'm creating an ND array with the values 3, 4, 5, 6?
Correct. And if you convert that to, let's say, 30 or 300 for the first 3, does that mean that 4, 5, and 6 also get changed? I don't know if that makes sense.
Okay. So this will certainly work. It will create an ND array of 4 int32 values, 3, 4, 5, 6. If I simply change this 3 to a 30, 30 is still an int, so I'll still have 4 int32s. If I change this first one to 30.0, now everything is going to be a float. Yeah.
What if one of them is a string?
Then they all get treated as strings, because a string is considered to be more complicated than an integer or a float. So let's do that one. Okay, so this will work, but it may, whoops, I forgot my opening square bracket for my list. All right, so I'm creating an ND array from a list in which I have a string and 3 ints. Now the string is the most complicated type in NumPy's reckoning. So I now have an ND array of strings. Okay? Which is probably not too useful a thing. I mean, the whole reason for wanting to use this very efficient representation of numbers is so that you can do fast calculations and fast searches, and so creating an ND array of strings is maybe defeating the purpose of using ND array at all. You can do it, but you probably are going to lose. You're going to probably lose some speed advantage, because the fastest access within an ND array is going to be to numeric data types. Okay. Now, here we have some list operations that we're trying to perform. Times of a list is interpreted to mean concatenation. plus between two lists is also interpreted as concatenation. Actually, I'm sorry, this first one, technically it is concatenation, but it's usually called repetition. You're repeating ls twice. You can't do a plus gets of an integer value into a list. That's an error. But for an ND array, these things are defined. Let's see. I have this array A, this ND array A, and if I say A times gets 2, this is not repetition. What literally is going to happen here is that each of the elements, each of the items within the ND array is going to be multiplied by 2. This is what's called a vectorized operation. So the scalar 2 is going to be multiplied into every element in that array A. And if I say A plus gets 1, a similar kinds of things happens. 1 is going to be added to each value within the array. And if I do the sum of two ND arrays, I get a vector sum. I don't get a concatenation. Okay, so A plus A is 22, 30, 38, and so on. However, notice that didn't change A itself. I would have had to say A gets A plus A to actually alter A. Okay, so if you just remember that ND arrays behave like vectors, then scalar multiplication, and addition and division and so forth will make sense. You can also request slices from an ND array using the index colon index kind of notation. But a very important distinction between ND arrays and lists is that if you ask for a slice of an ND array, that's not creating a separate sub-ND array copy. It's actually just giving you a view on part of the underlying ND array. So let me create A2 here as np.arange10. All right, so A2 is 0 to 9. I can ask to see just A2 sub 2 colon 7. And that gives me from item sub 2 up to but not including item sub 7. Whoops, too much highlighting. All right, so I need a better touchpad, I guess. All right, so I got 2 through 6. However, that's not an independent array. And if I say something like A2 sub 2 colon 7 gets minus 8, that's actually valid, but what it does is it changes the underlying ND array A2. So now all of the items A2 sub 2 up through and including A2 sub 6 have been changed to minus 8. So that's either, well, it's a feature, but it's only a feature if you remember that it's a feature. Otherwise, it's a bug. Okay. If you do want to get an entire copy of a slice, then you need to use this method .copy. All right, so here's my A2. And if I ask for A2, oh, we're calling it A4, I guess. A4 gets A2 sub, let's say up through 5, .copy. Now A4 contains 0, 1, minus 8, minus 8, minus 8. But if I modify A4 by adding 5 to each element, that did not modify A2. A2 is unchanged. Because I used the .copy method to create a brand new copy of that view. Okay. Well, so those were examples involving one-dimensional ND arrays. But the whole point of the ND array type is that you can have n-dimensional arrays, so you can have two-dimensional, three-dimensional, four-dimensional ND arrays. And you can create these things easily using iterables. For example, a list of lists, or a tuple of tuples, or a list of tuples, or a tuple of sets, or whatever. The restriction is that if you use something like a list of lists, then at the innermost dimension, the lists have to be the same length. So if I say A1 gets np.array, and then I create a list of lists, all right, so 0, 1, 2, 4, 6 is fine. And then as my second list, I'll say 1, 3, 12, 47. Okay, there I have a list of lists, and these two innermost lists have the same dimension. They both contain 4 items. So this is going to create for me an ND array of 2 rows and 4 columns. And in fact, I can find out how many dimensions the ND array has with ndim, or the specific number of rows, columns, out to the 3rd or 4th or 5th dimensions by asking for the shape. So A1 here is a 2-dimensional ND array, and in particular, its shape is 2 rows and 4 columns. Let me just point out one sort of peculiarity here, which is that ndim is not a function, and shape is not a function. Ndim and shape are both attributes of the ND array. Ndim is just an integer value, and shape is a tuple. So even if I have a one-dimensional ND array and I ask for its shape, okay, let me ask for its ndim. So the dimension of a one-dimensional array, I'll get there. The dimension of a one-dimensional array is just 1. And the shape of a one-dimensional array is, remember that a one-tuple is indicated by having a comma after the last value. So there are 5 columns, or 5 values, in this one-dimensional ND array. All right, so ndim is always an int, shape is always a tuple, even if the shape is one-dimensional. All right? Now, you can use the reshape function to change the shape of an ND array. That does not actually change the shape of the existing ND array, but what it does do is to create a new ND array in the different shape. So here I'm going to create A2 as a one-dimensional ND array of 12 values. And now I can convert that into a 2x6 array, or a 3x4 array, or a 4x3 array, or what have you. So let me say A3 gets A2.reshape 3, 4. I want 3 rows and 4 columns. All right, so A2 is still one-dimensional, but A3 is now 2-dimensional. Or I can say A4 gets A2.reshape 6, 2. Make sense? All right. Yes.
So what if we could not evenly split them into
That's a good question. Then it will just fail. So, for example, if I try to say A5 gets A2 dot reshape 9 by 17, just to pick a couple of numbers, I get an error. So the reshaped array has to have exactly the same total number of elements in it that the original array had. So I didn't choose 12 by accident. So by the way, do you know what's cool about 12 and 360? Why are there 360 degrees in a circle? 12 is 2 squared times 3. 360 is 2 cubed times 3 squared times 5. Lots of divisors in those numbers. You can forget that immediately. All right, so we've looked at two different ways of creating ND arrays. We've got the A range, and we've got array, which takes an iterable. Here are some more ways of creating ND arrays of specific kinds. You can create an ND array of all ones, or of all zeros, or of any value that you want by specifying the value. You can create identity matrices, identity ND arrays, either using I or identity. These two functions do exactly the same thing. So you just use whichever one you think of first. Now the shape here is a tuple, so I would have to say NP, let's see, A 5 by 5. Okay, I can use X in a variable name, so A 5 by 5 is NP dot ones 5 comma 5 is my shape, and now I have a 5 by 5 array of ones. If I say NP, come here, NP dot I 6, okay, I get an identity ND array 6 by 6. Yes?
Does it always make them floats?
It does by default. It does by default. Okay. You can change the type. You can say np.I, and notice in the help message. Now, if I try to click on the help message goes away, which is annoying. But I can specify the data type. The default is float, so I can say, give me an identity matrix that's, let's say, 8, where the D type equals, and you don't have to type out the angle brackets and class and all that rubbish. You can just say D type. Actually, I can't use int, so I'm going to have to say np dot int 32, I think. There we go. And so now I got an ND array of integers instead of floats. Okay. All right, now if you have a multi-dimensional array, it turns out you can do multi-dimensional slicing within that array. So here I've got a revised A1, which is going to contain np.array. Now you'd think I would have been smart enough to type this in advance, but I wasn't smart enough. Okay, so now I have an ND array of 3 rows with 5 columns, like so. And we know that with a one-dimensional ND array, I can ask for a slice by just specifying 1 range using the colon. So I can say, come on, A1 colon 3 to get a slice of these two items. Now the same idea is true for multidimensional slices. You can say A1 sub 1 colon 2. That's going to give me from row 1 up to but not, well, it's going to look strange. Let me say 1 colon 3. From row sub 1 up to but not including row sub 3. So we're going to get row sub 1 and we're going to get row sub 2. There is no third row, so that's fine to stop at 3. And let me get from column 2 to 4. Okay, so here is how I can ask for these 2 rows, but only these 2 columns within those 2 rows. Okay, so you just specify multiple slices between the square brackets with a comma in between to separate the row slice from the column slice. This is a view, so if I say A1 sub 1 colon 3 comma 2 colon 4, let's say times gets minus 2, that does change A1. All right, these 4 items that were in that slice do get multiplied by minus 2. Okay, and on slide 51 here we have a similar example. Here we're just saying 1 colon, meaning from row 1 all the way up to the last row. And then colon 3 means from the beginning column up to but not including the third column. So this is, in this example, it's going to be these values. Okay. Now, A1's dimension is going to be 2. A1's shape is going to be 3 by 5 as a tuple. I can access individual items by first asking for a particular row and then asking for a particular column. All right, so A1 is the whole thing. A1 sub 1 is just row 1. A1 sub 1 sub 4 is the sub 4 column of row 1. Now that's just an integer, and so what I get back from that is just an integer value. Okay, notice that A1 itself is 2-dimensional, but A1 sub 1 is 1-dimensional, and A1 sub 1 sub 4 is a scalar value. Good? Yes?
How come there are 2 different ways of defining the syntax is the same, as in having 1 square bracket and a number, and then another square bracket and number, and also the square bracket and number.
With a comma?
Yeah.
It's that's a good question. I mean, it's simply okay. So I can say A1 sub 1 comma 4 to get the same thing. They accomplish the same thing. They accomplish the same thing following different pathways, I guess, if you will. This notation here is directly treating A1 as a 2-dimensional object and getting one particular scalar out of that 2-dimensional object. This approach here is extracting from the 2-dimensional object a 1-dimensional subset and then extracting from that one-dimensional subset a scalar value. I get to the same place, but it's that's a really good question. Yeah, I should have been more clear about that.
Slices it twice.
Yeah. Yes.
In slide 51, could you please explain how does that multiplication work one more time?
Oh, sure. Okay, so times gets and then minus 3 means that each value that's currently in that particular slice of A1 is going to be replaced by itself times 3. So, in other words, if I say x gets 12.5, and I say x times gets minus 3, that's the same thing as saying x gets x times minus 3. It's just that in this case we're using a view. So let me make a copy of A1 so I don't screw up A1. So A1 copy equals A1 dot copy. I can find out for sure that these are separate from each other by checking their IDs. Okay, the IDs are different, but the values match. Okay, so all the cells have the same value. Now I can say A1 copy times gets 2, which is equivalent to saying A1 copy gets A1 copy times 2. Now this is a matrix times a scalar, and so it's doing like, matrix times scalar result, and that's getting put back into A1 copy. And that certainly works. So all the values have been doubled. But I can also ask for just a slice. I can say A1 copy. Let's see. Let me ask for all of the rows up to but not including row sub 2. And let me ask for all of the columns up to but not including column sub 3. What's that going to be? Well, okay, so I'm going to get row 1 and row 2, but I'm only going to get columns 0, 1, and 2. Whoops. I'm only going to get columns 0, 1, and 2. So those 6 cells in the upper left, more or less quadrant, I mean it's a little bigger than a quadrant, those cells I'm going to multiply by minus 1. Okay, so these cells have now been negated. Did that help? Okay? Okay, I'm trying to decide whether these last couple of examples matter. Here's what I'm going to do. All right. I showed you that from A1, I can get one cell from that by saying A1 sub 1, 4, and that gives me a scalar, correct? But what if I'm looking at documentation for a library function? The library function tells me that it requires a certain argument to be a two-dimensional array. Well, you can certainly have a two-dimensional array that only has one row and one column in it, can't you? So how could I get that value 125 in the form of a two-dimensional array? Here's the trick. I can say A1 sub 1 colon 2. Now, when I say 1 colon 2, that means from row 1 up to but not including row 2. So that means just row 1. But it will be as though that's a matrix containing just a row. And then I can also say, for my column, 4 colon 5, that means, all right, so I want all the rows from row 1 up to but not including row 2. And from within that, I want all of the columns from row 4 up to but not including column 5. This is going to give me a two-dimensional array that only has one value in it. Okay, so in other words, the number of dimensions of this is 2, and the shape of this is 1 by 1. All right, so that's a trick for obtaining a, if you've got a two-dimensional array and you want a two-dimensional subset of the array, but you only want there to be one value within that two-dimensional subset, you can use this trick of slices that are only one row long and only one column long, and end up with a single cell, but two dimensions. All right, so that's what these next few slides say in more bloated notation. All right, so next up I want to look at what are called Boolean indexes. Boolean indexes are another way of subsetting an ND array. We've looked at slices, that's one way. Using Boolean indexes, I can use true and false values to indicate which rows or columns I want to get. All right, so here's my A1 array. And let's suppose that I only want the first row and the last row. That is, I want to get rid of that middle row. Now, there's no slice notation that I can use to get rid of that middle row. So here's where Boolean notation comes in, or Boolean indexes. I can say B rows. All right, I know that it looks like browse, but I promise it's B rows. Is true, false, true. I've defined B rows as a tuple of 3 values. It could be a row of 3 values. It could be an ND array of 3 Boolean values. And if I now use B rows as an index into A1, wait a minute, why didn't it work? Can't it be a tuple? Okay, apparently it can't be a tuple. I thought it could, so I will do what the notes describe. Same idea, but we're going to have this be a list instead. I'm going to have to reinvestigate that. So now if I say A1 dot, so B rows, I do get just row sub 0 and row sub 2. The row where the Boolean index was false just gets left out. This is also a view. It's not a copy. So if I wanted A1C to be a copy, I would say A1 so B rows dot copy. Okay, so A1 is unchanged. A1C is separate, and it's an array of 2 rows with 5 columns. Yeah. You can do the same thing for columns. like so. Let me create bcalls gets true, false, false, true, true, to indicate that I only want to get column sub 0, column sub 3, and column sub 4. Then what I have to do is to say A1 with a slice including all the rows, followed by my Boolean columns set, my Boolean columns list. And so there I get all the rows, but I only get columns 0, 3, and 4. All right, so you can get subsets of an ND array using slices. You can also get subsets of an ND array using Boolean indexes. The third way that you can get subsets of an ND array is to use what are called fancy indexes. And I'm just going to hastily show you one example of this. Here's A1. Let's suppose that I want not only to get just certain rows, but I also want to change the order of those rows. All right, I can say A1 sub, and then sub 2, 1, 0. This is going to get me just rows 2, 1, and 0 in that revised order. So in effect, I've swapped the orders of the rows by using this so-called fancy index, specifying the ordering of the rows inside of a list. I can duplicate things and I can leave things out. So I could say 2, 2, 2, 2, 0. Now I'm going to get no copies of row 1. I'm going to get 4 copies of row 2 followed by 1 copy of row 0. All right, so we have slicing, we have Boolean indexing, and we have fancy indexing. I have run out of time. What I'm going to do this evening is post a video covering more examples of Boolean indexes and fancy indexes so that we will know what we need to know from this material. Okay? Any last questions? Alrighty. I know you have stuff due tomorrow. I will be around via email to answer any questions that you do have. And I also want to remind you that what you turn in tomorrow is a draft, so you can change your mind later. All right.